Good afternoon. Welcome to Saturday Talk. We have Andy Mahoney here speaking. He's from UA Fairbanks. He's been working on ice for a long time. So thank you, Andy.
Hey, thanks, Mark. And so what I'm going to talk about today is sea ice in sort of in its global sense, why it's important globally, why sea ice often makes the news, but then some of the story behind the story that a lot of the larger media reports miss about how sea ice is important locally, and what's going on here in Barrow, both in terms of the changes that we're seeing and the science that we're doing here in Barrow in partnership with the community. So I'll start out, I'll give a bit of a background to sea ice, why it does seem to get into the news so often, particularly in recent years. I'll make a brief comparison between the Antarctic and the Arctic. That's a question I get a lot. I spent the year down in Antarctica in 2009, so I've been able to do a direct compare and contrast exercise myself. And then I'll zoom in here in Alaska, particularly in Barrow, to look at what the local impacts are of the changing sea ice environment. So I think one of the main reasons that sea ice captures the news stories is its integral role in the Earth's climate system. It has a strong feedback relationship with the climate in that as sea ice retreats, it tends to have a warming effect on the global climate, which of course, as you're probably aware, as the global climate warms, sea ice is more likely to retreat. So one of these processes is the ice albedo feedback process. This is the scientific name for the fact that ice is by and large a pretty white surface to have on top of the ocean. Reflects up to 90% of the solar energy that lands on the ocean. If you take sea ice and remove it from the top of the ocean and you replace it with open water, then you're replacing it with a surface that absorbs 90% before it lands on it. So the Arctic and the Antarctic have sometimes been called the air conditioners of the Earth's climate system. In these regions, they cannot typically absorb a whole lot of sunlight, which means that they're a net loser of energy from the Earth's climate. The Earth tends to warm up, it absorbs more heat, but then it can shed in the equator. That heat is transported to the poles, and that heat is lost from the poles. The way that it gets from the equator to the pole, a lot of that heat is transported through the global thermohaline circulation. This is the global conveyor belt of ocean water that transports heat from the tropics around the equator, heading both north and south towards the poles, where that ocean loses its heat to the atmosphere and ultimately out to space. This global thermohaline circulation is driven in large part by sea ice production. Ice is a crystalline material which cannot really contain anything other than water in its crystal structure. So it tends to reject all the other minerals and ions and salts that are absorbed, that are dissolved in seawater, and it rejects those into the seawater when it freezes. So immediately underneath sea ice you have water that is cold because it's freezing, and very, very saline because the salt is being rejected from the sea ice. Cold, saline water is going to tend to sink, and as you sink water in the northern regions, particularly here in the North Atlantic, and then down, you can't see the southern hemisphere here, but in the Weddell and Ross Seas in the Antarctic, when you push water down there, that's like a pump that then drives the whole circulation of ocean heat transport globally. So sea ice is related to both these very important sort of climate regulating processes. A lot of people think of the Arctic and Antarctic as fairly cold and lifeless, but actually there's a diverse and blooming ecosystem that I am certainly not the best person saying that in this room. But sea ice is actually a substrate for primary production. There are algae that live in the sea ice that get released into the ocean when the sea ice melts in springtime, prompting a bloom of algae and then all the other sort of species higher up in the food chain that creates an abundance of food for all the other animals that live in the polar oceans. in particular marine mammals, such as this is a Weddell seal that I saw in Antarctica, and then of course there's the polar bears, the walrus, the bowheads, all the other sort of iconic marine mammals of the Arctic. And then of course sea ice has a direct impact on human activities, primarily in the Arctic, just because there's so much less human activity in the Antarctic. But in the Arctic, it's used as a platform for hunting and traveling, both by indigenous communities and in industrial and commercial activities in the coastal regions. So why has sea ice been in the news? Well, largely because of dramatic changes that have taken place in the Arctic in recent years. The graph here shows Arctic sea ice extent as observed by polar orbiting satellites. So these are satellites that circle the world. They give us a global view of sea ice. We can add up every piece of sea ice that we can see. But the trend that we see from a decrease of over 8 million square kilometers of summertime sea ice, that's sea ice that's left at the end of summer, down to in 2007, it was 4.1 million square kilometers on September 26, 2007. This is a monthly average sea ice extent. So the average for September was more than 4.1, but the actual minimum that was reached in September of 2007 was 4.1 million square kilometers. But we went from an average back in 1979 of over 8 down to in recent years we're hovering around about 5 or 5.5 million square kilometers of sea ice. That decline is far bigger than any other possible errors that we have in our measurements. And for that reason, this is why sea ice has become such a news item in recent years. There was a fairly recent study back in 2009 that looked at changes and differences in the atmospheric circulation around Antarctica, and they found that related to changes in ozone depletion and changes in the wind in the upper part of the troposphere, there was a change in circulation that was causing a lot of wind to come directly off the continent in the region of the Weddell Sea. That wind coming off the continent is essentially pushing the ice away from the continent and spreading it out. And that's one idea as to why people think that the Antarctic sea ice isn't responding in the same way as the Northern Hemisphere. Because there's nothing to stop it spreading out further and further, there's no land surrounding it, it can mitigate the effect of losses that would impact the Arctic by just sort of spreading itself out to accommodate the losses of sea ice. The Arctic, when you look down on the top, so this is the North Pole right in the center of the image here, surrounded by the countries of the Eurasian Arctic, the North American Arctic, and Greenland down in the middle there. Looking down on it, the Arctic is an ocean surrounded by land. If we take the same view, or the opposite view, in the Antarctic sea ice is in an ocean that surrounds a continent. So completely opposite oceanographic conditions. Now there are other differences between the Arctic and the Antarctic as well. In the Arctic, and perhaps the most famous marine mammal, the most famous species is maybe the polar bear. Whereas in the Antarctic, I'm sure many of you are aware, they don't have any polar bear, they have lots of penguins. So maybe polar bears are melting the sea ice. But actually, no, another big difference between the Arctic and the Antarctic is the Antarctic continent is surrounded by ice shelves. Half the coastline of Antarctica isn't actually land, it's ice shelves. This is ice that's formed on land, it's snow that falls on snow that fell on snow that fell on snow over hundreds of thousands of years. This ice flows off the continent and ends up forming a floating shelf of ice that surrounds the continent. And like I said, half the coastline of Antarctica is made of these ice shelves. Now, I spent a whole year down there studying the next process that I'm going to summarize in one slide. Okay, have you all got that? Essentially, if you stick a big, maybe 300 meter, 1,000 foot thick piece of ice in the ocean through some properties of seawater. The melting point down here will be colder than the melting point up here. And that allows you to take water from down here, bring it to the surface, and it actually ends up becoming super cool. You can take water from depth, bring it up to the surface, and it's actually below its freezing point. As it rises and becomes super cool, you can actually nucleate ice crystals within the water column, which will then, being ice being more buoyant than water, will have a tendency to rise to the surface and actually collect underneath the ice shelf and underneath the sea ice at the surface. So next week we had a little video here of what the bottom of the Antarctic sea ice looks like. Now, I'm not sure how many people have seen what the bottom of Arctic sea ice looks like, but take my word for it, Arctic sea ice does not look like this. These are crystals about the size of your hand, sticking down, sort of somewhat higgledy-piggledy underneath the bottom of the sea ice. And that was us drilling a hole through the ice to measure the thickness. We're now lowering a tape with a bar on the end to measure the thickness. And you can see that we're disturbing these somewhat delicate ice crystals that are frozen onto the underside of the sea ice. And you can see as we sort of disturb them and knock them down, they of course have a tendency to float back up. So the Antarctic has this process whereby it can actually sort of generate its own sea ice through its ice shelves that surround the continent without relying on the way the Arctic has to form its sea ice, which is through losing heat from the ocean to the atmosphere. If you like, this is a way of getting free sea ice. You don't have to exchange heat with the atmosphere to get it. And this process doesn't exist in the Arctic. Okay, so now I'm going to come back to Arctic sea ice. And to me, the biggest difference between the Arctic and the Antarctic is the presence of people. The only people who are down in the Antarctic are a bunch of scientists with maybe a screw loose because they wanted to go down to Antarctica. In the Arctic, you've got communities who've lived on the coast and used sea ice for thousands of years. And that means that there's a huge storehouse of knowledge that, to a large extent, has not been tapped into. And I think that there is a change underfoot, and I think partly because sea ice is in the news, people are thinking about the Arctic a bit more. There's more and more effort underway to really tap into the traditional knowledge of the people who live in the Arctic. A concept that came up a lot in the three Arctic communities that I've worked with very closely is the relationship between sea ice and freedom. When the ocean freezes over, it opens up a whole new set of travel options. Places that before you'd have had to use a boat or may even have been completely inaccessible by any other means often become the easiest way to travel in the wintertime. This is a young hunter in Greenland who just returned from a several hundred-mile solo dog sled trip, and that's quite routine up there. It allows travel between communities, so it's a time when you can see friends and family from other parts of the Arctic. This is some GPS data collected by local hunters in Clyde River and sort of compiled by a colleague of mine, Sherry Gearhart, who lives in Clyde River, which is in Baffin Island in northern Canada. And you can see that they're traveling extensively over the frozen fjords because the option is terrain like this. Sea ice allows you to travel seamlessly between the land and the ocean. So places where you couldn't get to with a boat because you'd have to land the boat somewhere and then go inland or something. Trips become possible in wintertime that you couldn't do by any other means in summer. And this all adds to the concept of why sea ice, I think, is associated with a sense of freedom for these communities. And right here in Barrow, sea ice provides direct access to hunting grounds. These, many of you may be familiar with these maps used by the local crews to get from the land out to their whaling camps at the edge of the landfast ice. So the landfast ice is this extent of sea ice that doesn't move. It's attached to the coast, and if you get to the edge of it, that's where you're going to find the whales. That photo I showed of the whale being cut up earlier, that was at the edge of the landfast ice. So here, the sea ice allows you access to the hunting grounds that you wouldn't have access to were the sea ice not there. So I'm now going to focus on, I'm going to zoom in here in Alaska, and particularly here in Barrow, and I'm going to talk about this landfast sea ice. This is the ice that's attached to the coast. In terms of the area of the Arctic, only a small amount of it is actually composed of landfast sea ice. The vast majority of Arctic sea ice is drifting. It moves, changes position, changes appearance on a daily basis. Cracks can open up. A piece of ice can move up to 20 miles in one day. The landfast ice stays where it is. It's attached to the coast, and therefore is the kind of ice that most people come into contact with. Here in Alaska, it's characterized typically by ridges. These are ridges of ice that are formed by pressure between two ice flows. Two ice flows come together, they break apart, and they pile up much like a mountain range. And what you see on the surface is actually only a fraction of the ridge that exists underneath the water. If the ridge becomes high enough, and therefore deep enough as well, the ridge will actually sit on the seabed, become grounded, and this is what provides an anchor for the landfast ice and stabilizes it. What makes an event like that happen? We need to think about what makes the landfast ice attached to the coast to start with. I showed a diagram earlier that showed these grounded ridges, the ridges that get so thick they actually end up sitting on the ground. They can become grounded in two ways. We can either have a big old ridge that's formed somewhere offshore and gets blown by currents or the wind and comes into shallow water, and it'll sit on the ground and it'll leave a big gouge behind it when that happens. Incidentally, this is a major concern for any pipeline or cable that you want to run underneath the seafloor. The other way you can make a grounded ridge is if you just pile up the ice in place. It doesn't come in from offshore. So this is a ridge that's created in situ. And I need to do more work on this, but I'm speculating that you don't get the same kind of gouging on the seafloor if that happens. And that has, as I mentioned, that's important for seafloor infrastructure, but it may also be important for the benthic ecology, the creatures that live on the ground, on the seafloor get disturbed. So if we want to know where the grounded ridges are, we need to know how thick the ice is. One way we can do that is drilling through the ice, but that can get quite difficult when you've got ridges that are maybe 60 feet thick. So instead we use this electromagnetic device. It sends out an electromagnetic field which creates electrical currents in the seawater underneath the sea ice. And we can measure the strength of those currents. And the strength of those currents is proportional to how far away the seawater is. Or in other words, how much sea ice is between you and the seawater. Now, if you talk to whaling captains and hunters who go out on the sea ice a lot, they'll tell you that they're always watching the weather, they're watching the clouds to see which way the wind's going, in particular which way the winds are going near the surface and which way the wind's going up higher. That allows them to maybe make some predictions about what wind might be coming a few days from now. But they also say that they look for what the currents are doing. And I was told time and again that the currents are the most important thing. Unfortunately, they're probably the hardest thing to measure as well. If you put an instrument on the bottom of the ocean, you stand a risk that it's going to get cleaned off the bottom by one of those grounded ridges that I was showing you earlier. If you put the instrument in the ice, well, then you run the risk that the ice might break away and you never see your instrument again. Or a ridge might form on your instrument and you might be able to find the instrument again, but it's not going to be in any shape to tell you anything. But recently, we entered a collaboration with some Japanese colleagues. We got some money from the National Science Foundation who agreed that it was worth the risk to try and put some moorings on the bottom of the sea ice, on the bottom of the ocean underneath the sea ice. And we've now had 2 successful years. This was a photo just the other day when we were retrieving our moorings that have been under the ice all year. This is a mooring that just popped up. It had been sitting there since about the same time the year before, collecting data right from underneath the ice, the area, the type of data, and from the place that local experts are telling us we really need to know that if we're going to understand the changes that are taking place here in Barrow. So this is hot off the press, never been shown to the general public before. Water temperature and current speed. Starting from when we deployed the mooring back in early August last year, through till July this year. And you can see when we deployed the mooring, through till getting into September, October, the ocean temperature was around about 5 degrees C. Then we had sea ice start to form. The ocean loses a lot of heat, and it's then obviously cold through the winter time, and it starts heating up again in the summertime. These regions here, where the temperature is very, very stable, the water is at the freezing point. You can't cool water below the freezing point if you don't have those ice shelves that I was showing you down in Antarctica. So you can't go any colder than this, and that's why the water hits that temperature and stays there. Now, to be honest, I expected to see this from January through till April. Instead, what we see is significant warm pulses. Now, when I say warm, okay, I'm talking 0.5 degrees C, so we're talking 33 Celsius or something. Now, that might not seem very warm, but for sea ice, that's over a degree warmer than its freezing point. That means you're going to be melting sea ice when you have water that is this warm. Now, frequently, these warm pulses are actually associated with very strong currents too. This is a current of about 1 meter per second. And that doesn't sound like a very strong current maybe, but if you think of that in atmospheric terms, if you think about the drag that is exerted on the sea ice, that would be the equivalent of a 50 or 60 knot wind. And if you think about the amount of heat that you can transfer with a current that's that strong, even though you only have a very small spike in temperature, that can actually deliver a substantial amount of heat to the bottom of the ice. And this may also be contributing to the erosion of these keels, these grounded ridges that are stabilizing the sea ice. So this is new data. We've got a lot of work to do to really understand what it's telling us. But we are surprised by 2 things. One, the number of these little warm pulses through the year, and also the speed that the current got up to at times. That both of those were quite surprising to us. Though I should point out, probably not so surprising to a lot of the local experts who've actually been telling us this for some time. So I sort of want to finish up saying that this work is part of a much larger network. SeisONet is the Seasonal Ice Zone Observing Network. And we're working with people in Wales and Gamble. We've actually got partners in Japan as well who are part of SeisONet. SeisONet itself is part of the Arctic Ocean Observing System, which is a global effort to try and better understand the changes that are taking place in the Arctic and provide information to local communities and decision makers on a global scale. Here in Barrow, in addition to the radar, the webcam, the ice thickness surveys, the moorings that I've already mentioned, we've also got ongoing remote sensing efforts. We have a sea level gauge that we put out each year in the wintertime. We carry out interviews and we have local ice experts keeping almost like an ice diary for us. This is Joe Levitt on the right. He's a key member of our local observing team. And then we also have an ice mass balance site which we put out in January. And, so to sum up, the Arctic is experiencing ongoing retreat. The scale of the retreat is far bigger than any uncertainty that we have. I mean, this is real, it's going on now. Antarctic sea ice is not retreating, but we may just be on borrowed time. It may not be retreating because we're actually spreading it out, not really necessarily making new ice, we're just spreading out the ice that's there by these winds that I talked about. And then there's also this mechanism where you can take ice from the bottom of the ice shelf and pump it up to the sea ice. But again, that's not really stopping the ongoing change, that's sort of just borrowing ice from one place and putting it to the other, giving it to the other. So we may just be on borrowed time with regard to changes in the Antarctic sea ice environment. The local residents here in Barrow, or in the Arctic, and particularly here in Barrow, are already feeling the impacts. And so we have a need for observing programs like we're involved with, like the community here in Barrow is involved with, to provide the kind of information that people need to make decisions about changes now